Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today's lecture. Our today lecture is about the semiconductors. It is lecture number 39, unit 16. So let us start with the name of Allah Almighty. Bismillahirrahmanirrahim. Semiconductors. Class, I told you in the previous lecture that semiconductors are those substances which have resistivity intermediate between conductors and insulators. Semiconductors. Semiconductors. I'm sorry. Okay, then I told you that semiconductors are that is the example of the semiconductors include, for example, they belongs to group fourth element, belongs to group fourth elements, belongs to group fourth elements such as, for example, germanium and silicon. They have their four valence electrons. They have four valence electrons. So their outermost shell contains four electrons only. And they are covalent bonded, right? They are what? They are the covalent, they have the covalent bond structure. Covalent covalent bonded, or they have covalent bond structure. At room temperature, they perfectly behave as insulator. Now we have two different types of semiconductors which I'm going to explain here. The first one is the intrinsic semiconductor substances. Intrinsic semiconductors. The intrinsic semiconductors. One, we have the extrinsic semiconductors, and the other we have extrinsic semiconductors. So before going to explain the intrinsic and extrinsic semiconductors, let us see here. As I told, for example, I have taken I have chosen the example of the silicon, which has atomic number 14, and you see that the silicon atom has 4 electrons in their outermost shell. So at room temperature, as you see, all the 4 electrons are bonded together. For example, look at the central germanium. So due to their covalent bond structure or the sharing pair of electrons, here you see, look, they all share the electron with, as you see here, look, and see here like this one. So they, this one, this electron, this electron, this electron, this electron, and this electron, as you see, due to the sharing pair of the electrons between them, as you see here, the covalent bond structure. Now, normally their octet is complete, right? They have the 8, like it seems like 8 electrons in their outermost shell. So this is a kind of, you see that we do not have any free electrons here, and at room temperature they perfectly behave as insulator, right? So this is the way the silicon atoms behave. Now what happens, that is that, let me tell you that how the intrinsic semiconductors are. That intrinsic semiconductors are usually the semiconductors in pure form. So they are actually pure semiconductor, pure pure semiconductors, right? And normally they do not have the free electrons, right? But they have only the they have only the thermally generated, they may have only thermally generated electrons, thermally generated electrons, they have what? Thermally generated electrons. Now what does this means? That it means that the electrical conductivity, the electrical conductivity the electrical conductivity of the semiconductors intrinsic, right, of the intrinsic semiconductor increases with increase in temperature, with increase increase in temperature. So if you increase the temperature, then their conductivity increases. So here you see, look, now what going to happen, that here is the thermal conduction. Now when you increase the temperature, then the covalent bond structure breaks, a hole and electron pairs created, and you can say that the electron from its place, as you see here, right here, this one, that dismantle from its position and can become the source of current, or can be the current carrier. So we have here the current carrier are the thermally generated electrons. So when you apply an external electric field across the such conductors, then they will allow the current to flow through. So here mm, the current carrier are actually the thermally generated electron hole pair. Clear? So this is how, or this is one of the reason in which we can increase the electrical conductivity of the semiconductor substances. So if you remember, when I was teaching to you the coefficient of electrical conductivity, then at that point I told you that such material have negative coefficient of thermal conductivity, that increase in temperature does not increase resistance, rather decrease the resistance, and current is generated. They are, since as I told that they are covalent bonded structure, so no need to write it again. And then I told 4 valence electron. One important point is that they have intermediate energy gap, and I don't need to explain the energy gap again. Intermediate energy gap, right? The energy gap is small, and this energy gap is of the order of the mm, electron volt. And here and another important point here, the number of electrons in the conduction band, the number of the electrons in the conduction band is the same as the number of holes in the valence band, right? That is the one of the important point about the intrinsic semiconductor. And they have very low conductivity, very low conductivity, very low conductivity at room temperature, very low conductivity at room temperature. They have very low conductivity at room temperature, right? And the increase in temperature increases the electrical conductivity and increases with increase in temperature, and increases with increase in temperature, which I already wrote there also. So that is all about the intrinsic semiconductor. Now we have the extrinsic semiconductors also. Extrinsic semiconductors. Extrinsic semiconductors. Now let me create some gap for myself here so that I may be better able to explain. Okay. The extrinsic semiconductor substances. So what are the extrinsic semiconductor substances? The extrinsic semiconductor substances, as I told, are the kind of substances are semiconductor in its pure form. Semiconductors in its impure form. How? Let me explain this to you. The extrinsic semiconductor is, they are formed, the extrinsic semiconductors are formed by the process called doping, by the process which we call doping. You might have heard about the dope test in some sports also. So they are formed by the process of what? By the process called doping. Now, what is doping? I'm coming to that point that doping is the deliberate addition. Doping is it is the deliberate addition of impurities to intrinsic semiconductors in order to increase its electrical conductivity without actually increasing the temperature, without actually increasing the temperature. This process is called the process of doping. We call this process as doping. And now let us see that these impurities, these semiconductor substances, depends on the kind of impurities or depends on the process of the doping. We have two kinds of semiconductor substances. They are, one we call the N-type semiconductors and the other we call the P-type of semiconductors, the P-type semiconductor substances. In the N-type semiconductor substances, that is the both for the N-type or the P-type semiconductor substances, the doping agent have different valence electrons than the parent materials. The doping agents have different have different, the doping agents have different valence electrons than the parent material, the parent the parent material. The parent material are the intrinsic semiconductor substances. So what are the N type of semiconductor substances? Let us explain the N type first. The N type semiconductor substances. Class, remember one important point, that both the N-type and the P-type substances, they both are electrically neutral. Both these substances are electrically neutral. Remember, they are electrically neutral. They both are electrically neutral. Now, what are the N-type of substances? The N-type substances are, I would like to tell you that in the whether if it is N-type or P-type substances, one important point I would like to share with you is this one, that the material have high conductivity. They have what? High conductivity. Whether N-type or P-type, they have very high conductivity. And more interestingly, the number of electrons are never be the same as the number of holes. Right? Now, what are holes? Let me explain to you this also, and then I will refer to the diagram. Holes are in fact holes. Holes when electron is removed, whenever, yeah, when electron is removed, it leaves behind, yeah, it leaves vacancy behind. A vacancy behind. The word hole is not good. I usually call it the vacant site. This is called the hole. It is called what? It is called hole or the vacant site. The vacant site. In a simple word, in simple words, I would like that it is just a seat of positive charge. What? A seat of what? A seat of positive charge. Positive charge. They do not have the positive charge. Holes do not, remember, hole do not have the positive charge, right? They do not have what? They do not have the positive charge. Do not have the positive charge, but seems to be like having the positive charge. Now, let me explain to you that for the N-type material, the doping agent, the doping agent is pentavalent impurities. Pentavalent impurities. What? The pentavalent impurities. Pentavalent impurities means that the impurities belongs to, that is from the group fifth, right? Just see here, like for example, look here we have the N-type semiconductor substances, as you see here in our diagram. Look, this one, this is the N-type semiconductor substances. Here you see that, look, we have the impurity as the lead, and this is the silicon atom. Now you see that it is pentavalent impurity. So all of its four electrons are what they are uh, bonded together with each germanium electrons in their outer valence shell. But look, since it has 5 electrons, so one electron is what? One electron is still remaining, right? That is called the donor impurity, which contribute, that is, and this contributes the free electrons or electron. The free electron are electrons. Here you see this electron, free electron. Since here the octet is now complete and this electron is free and it can move with an atom to atom to find a pair for itself. And when the electrical connection is established across such a conductors, then this free electron is the current carrier. So in n-type material, it is the free electrons are the current carrier. Free electrons are the current carrier, are the current carrier. Free electrons are what? Free electrons are the current carrier in this case. Now, in the n-type semiconductor substances, so we have the doping agent, the doping ratio, the doping ratio. That what is the doping ratio here? The doping ratio is that it is 1 ratio 10 raised to the power 8. That is for one germane, for 10 raised to the power 8 silicon atom, intrinsic atom, there must be one impurity atom. You may check your book for this one, the 10 raised to the power 8, as I wrote that whether it is 10 raised to the power 8 or 10 raised to the power 6, I'm forgetting, but 80% I'm sure it is 1 into 10 raised to the power 8. This is the doping ratio here. And in the n-type semiconductor substances, the number of free electron are far greater than the number of holes here. Okay, so the majority carrier are the free electrons here. Second, the thermal conductivity. Thermal conductivity, thermal conductivity is directly proportional to the number of free electrons. So what does this means? That it is directly proportional, in other words, directly proportional to doping. The greater the doping, the greater will be the thermal conductivity, right? As I told, for the p-type material, or for the electrically this is neutral n-type. Okay, for the p-type substances, for the p-type material, what do we have here for the p-type material? For the p-type substances, the doping agent here, the doping agent is actually trivalent material, trivalent substances. That is, here the doping agent belongs to the group 3 element, which have valency from group 3. Here the holes are the vacant site, holes are the current carrier. Holes are the current carrier here. So holes carry the current here. Okay, holes are the current carrier, right? And the free, that is the doping ratio, is the same here. Doping ratio, the doping ratio is again 1 ratio 10 raised to the power 8. Okay, and here the number of the hole is far larger than the number of electrons. Now let us see here for the p-type substances here. What do you see? Look, for example, here we have the bismuth and the which has the three valence electrons. So now all that is, it is surrounded by four silica atom, and you see that they are all bonded here. There is the this one of the electron is one of its electron is bonded with this silicon atom, one bonded with this, one with this, one with this. But for this, it doesn't find any pair, and there is created as what? They're created as a hole. This acts as acceptor impurity hole, right? And it is in search of what? And it is in search of, this is just as I told, that it is a kind of vacant seat and is in search of electron. Actually, there is no such thing which holes are moving. It is fixed at their position. But when the electron jumps from somewhere here, then at that point another vacant site is created, and it seems that as the holes are moving. Okay, in fact, holes are not moving. These are actually the electrons which are moving after the holes. So here, when you apply the external potential difference, then the current carrier in this case will be the hole. So holes are then the current carrier in this case. Okay, so this is all about what? This is all about the intrinsic semiconductor substances. And the next, and then we have the PN junction diode, and the next one, the PN junction, or the PN junction diode. This is also called the PN junction diode. Now, what is the PN junction diode? The PN junction diode is formed when P-type material is suitably joined with N-type, resulting in arrangement known as the PN junction diode. So that is here in the PN junction diode, what we actually do, that here neutrality, the neutrality is disturbed. Neutrality is disturbed. Okay, and we have what? And that is, and the such kind of substances, they may be used as two and one, both as a conductor and both as an insulator. It is just what I would like to tell you, that this is just like an equivalent of the capacitor. That is a smart or equivalent, or the equivalent to a capacitor. Okay, so inshallah, in my next lecture I will explain the PN junction diode in the great detail. Okay, so I think it's enough for now. So inshallah, see you in the next lecture.